All right, how's everyone? Hello, everyone. How's everyone? Good? Happy? Friday before long weekend, right? You should be. I am. So, about your week, about your week, so answer question 2 according to the TA or the rule. Was difficult? Okay, so we'll go easy on marking for that one. Yeah, I usually in term 1 I give a challenging question to pick where it is you are. But vibration usually after the midterm, you get the idea of the binding, you get the hang of things, how and you learn what is the pattern. In fact, if you understand what's going on, it's not a really difficult problem. And as I said at the beginning, I'm going to have a balance of math and concept, so you could get a good grasp of it. So don't worry about your midterm results. The TAs are marking them. Question 1 was okay. Question 3, in the hint. So some, like the buoyancy force, is the rate of the volume change. But if by mistake, instead of the rate of volume, injection is volume, I asked TAs that that's okay. So when they mark, it's not going to be any subtraction for that. Just get a weird number for that. But if your solution is correct, then that's okay. Okay. So it was important to understand when you put something inside the water, right? You press it down, it acts something like a spring, which goes up and down. The next time you are in the boat, you can notice it. So the boat goes up and down, and the boat goes down. Okay, so that's about midterm. Any question, concern, or anything that you were happy or unhappy? Otherwise, okay. All right. So let's continue with the topic that we started. So we switch to the topic where we add damping to the system, right? And we said damping or shock absorber is something that in most of the system, like a car or other system, it exists. And the most common damping is a viscous damping, which we said it creates a force which is unlike a spring. It has nothing to do with deflection, but with the speed. It creates a force which is, say the force was somewhere here. Yes, the force that the damping creates is a constant, which we call it the damping coefficient multiplied velocity. So we developed the equation of motion both with Newton and Lagrange, and we get to this one: mx double dot plus cx dot plus kx is equal to 0. From now on, our equation is going to be, looks like this standard form. Like before that, we didn't have this cx dot, right? But now we have that tab. So we plan to solve it, and the next step, right now it is 0, but next step we're going to have some force, excitation force. So we will add force. All the steps that we had before for system with no damping, we're going to repeat them here. So as you can see, slowly we are adding things to the system, right? And making things more ideal, closer to the reality. So let me repeat the equation again: mx double dot plus kx, not kx, let's write them in order, plus cx dot plus kx is equal to 0.
if I want to solve this equation, all right, I need to start with a guess. So I need to guess an answer for a solution. So this is the way that we solve differential equation. So I need a function that repeats itself when I take the derivatives, right? I want the function, then the first derivative, then the second derivative, and they should repeat themselves. If I start by sine, sine become cosine, and then become sine again, so I will be in trouble. I cannot get rid of that. So what should be a good function that can repeat itself when I'm taking the derivatives? Exactly, e to the power of something. So let's call it lambda t, because we have also time, right? And probably a constant, let's call that constant maybe a or x. This is just a constant. So that's our guess. This is a constant, and lambda is a constant. You can call it whatever you want. And t is time. Let's try our chance and see if really this is a good function for this differential equation. So if I take the derivative x dot, and by the way, I'm just lazy not writing the x dot t, but it is there because x dot also is a function of time. So x dot will be a lambda e lambda t, and x double dot a lambda square e lambda t. Let's substitute them and see what will happen. Ma lambda square e lambda t. Then I have ca lambda e lambda t, and then k a e lambda t equal to 0. Let's simplify it one step. I would get here a, and we're gonna have m lambda square c lambda plus k e lambda t equal to 0. So in order for this function to become 0, we know a cannot be 0 because if a is 0, it means the whole answer is 0, doesn't gives us anything. E lambda t is not 0, it's never 0. So my only chance to have this function equal to 0 is to set that equal to 0. M lambda squared plus c lambda plus k is equal to 0. So a simple equation, it has two answers, lambda 1 and 2, which is 2m minus c plus minus 4mk, right? So as you can see, this lambda can have different values, depends on m, k, and c. And as a result, the shape of the answer can be different, right? For example, I can have values, oh, this is minus. I can have values that gives me like underneath of that square root, a negative or positive or even 0. So I would say then the behavior of this response or the shape of this function that we guess depends on the value of m, k, and c, or depends on the solution of this equation. And this equation, we will call it then characteristic equation, because the character of system depends, or the behavior of the system depends on the character of this equation. So characteristic equation. All right, now let's delve into a little bit into this equation and see if we can get some insight out of it. So in this equation, something that pick our attention is this c squared minus 4mk, right? So I would write then c squared minus 4mk dictates the behavior of this system. it can be 0, minus, or positive. Zero, minus, or positive, right? So let's set it to 0, equal to 0. From here, I would get C equal to a square root of 4mk. All right. Let's call this C then a critical value, because this C determines that what I will get, like a negative number, a 0 number, or positive number. So let's call this value critical number. It is critical because if it changes, the behavior of the whole system changes. So we show it by C critical. And let's show it by C critical for mk. So remember, we have a system, it has a mass, it has a stiffness. Depends on how much is the mass, how much is the stiffness, I will get a C critical. So these C criticals then depends on my mass and my stiffness. So far, are you with me? So we have a value. It depends. We have nothing to do with this C. C has its own number. All right. We just calculate the number, depends on mass and K. And we call it a critical value because from the equation that we just drive here, we realize that it can has a significant effect on the behavior of the system. Now let's do one more step and try to define a ratio between this value and the actual value of the damping. So let's define the ratio C over C critical. So this value, it is a Greek letter, zeta, or you can call it Z. It has this like weird shape, Z, right? Zeta. You can just simply show it by Z. So this zeta, we'll call it the damping ratio. Damping ratio. So what is this damping ratio? This is the C, the actual value of the damping. Right? I have a system, depends, if you recall, I said this damping, we can change its coefficient by changing the size of those holes in the cylinder and piston and the type of oil that you put there. So this is a value. It depends on the manufacturing of the damping, and we have that number. C critical depends on the M and K of the system. We find this ratio, zeta. Now this zeta can have 3 different values, right? So zeta can be smaller than 1, it can be equal to 0, and it can be bigger than 1. Oh, sorry, 1. Just compare with 1. So 3 values, zeta less than 1, and zeta is equal to 1, and zeta is bigger than 1. So obviously when zeta is equal to 1, our damping is equal to the critical damping. When it is less than 1, it is less than critical damping. And when it is bigger than 1, it translates that the damping that we have is bigger than C critical. Right? So far, we haven't analyzed the behavior of this system. We just trying to build up these, let's say, or define this formula or these parameters. So then later we can treat the system. Right? So from now on, we're just gonna mention this zeta, but for you, they should have the meaning. When we say zeta is less than 1, immediately you should realize that, okay, my system has a damping that its value is less than C critical. What is C critical? It has its own formula, and we saw this formula is not just some magic number. It comes from this equation that we solved. All right. So far, any question? You're good? Okay. So now let's do one more step, and then we attempt to continue with the solution of that equation. The title of this page is the standard form. Let's manipulate that equation a little bit, make it a little bit maybe, I would call it sexier. Right now it's a little bit ugly. So what I will do, I divide everything by n. Let's do that. I would get x double dot C over m. This is x. K over m, x equal to 0. All right. So I know K over m is omega n squared. All right. What about C over m? Let's manipulate that one a little bit. C over m I can write instead of C, I can write zeta multiplied by C critical over m. All right. Remember, we have definition for zeta here. And for C critical, I can put the value 4mk over m. So I can simplify it a little bit. So it's going to be 2 zeta k over m. So it gives me 2 zeta omega n. All right? Yeah, looks good. So now let's substitute this C over m that we simplify it there. I will get x double dot 2 zeta omega n x dot plus omega n squared x is equal to 0. Do you agree? This one looks a little bit more advanced and sexier, right? It's scarier. People who looks at our notes, they realize, okay, this is advanced course. This is serious stuff. So, and this is the standard form that you're gonna work with it. And now you know where it comes from, right? Zeta has a definition. It is C over C critical. It can have any value less than 1, bigger than 1, or equal to 1. And it has a meaning for us. Omega n depends on mass and stiffness. And it has a meaning. It is the natural frequency of the system. Okay, so far good. If we are good, now let's try to solve this equation. Again, we repeat whatever we did above. X double dot plus 2 zeta omega n, x dot plus omega n squared, x equal to 0. So we repeat what we did before. It is just the shape of the function has changed. So guess an answer or a solution. We know the solution that we like. is, let's call it a e to the power of lambda t. Substitute it in this equation, right? So we have x dot a lambda e lambda t, x double dot is a lambda squared e lambda t. I'm just repeating what we had above, but this time it is a standard form. We substitute them there, we will get a 1 plus 2 zeta omega n lambda plus omega n squared, right? Over here, we will get, okay, this is lambda squared, equal to 0. E to the power of lambda t is equal to 0. From here, this is my characteristic equation, 2 zeta omega n lambda plus right? So when I see a new system, first thing that I will do after I write the equation of motion, I will calculate C critical. We have a formula for C critical, right? I will then calculate zeta, the damping ratio, and then I will calculate the natural frequency. I have these three numbers, so I have my characteristic equation, right? So I have zeta, I have omega n, and lambda is just a variable. So if we solve this one, we will get lambda 1 and 2 is equal to omega n minus zeta plus minus zeta minus 1. Yeah, okay. So we have two answers for lambda then, right? Because here we have plus and positive and negative. I just simplified, I factor omega n. But check my calculations, make sure that I haven't missed anything. Seems correct. Right. Now, and the solution will be, the solution will be, so I have two lambda. Then what is the solution? From your differential equation, do you remember? So here what we have, this is what we guess. And we were lucky, it gives us something. So it was a good function to start with. I have a e lambda t. I have two lambda here. What should I do? What is the answer? Which of them I should go with?
Linear combination.
Exactly. Thanks, Alberto. So when you have two, the superposition, the property of superposition, and as Alberto said, linear combination is your answer. So your xt then is A1, let's call it E lambda 1t plus A2 E lambda 2t. So this is the solution to this equation, differential equation. We left with two constants, A1 and A2, or let's just call them A and B, similar to what we had before. All right, A and B. So what should we do about A and B? Those constants? Exactly, initial condition. We can find A and B. From initial conditions. All right, so problem solved. If I know the initial condition, I have the solution then to my equation, and I can find these constant A and B. Let's, as a general case, assume that we have like this general condition as a general case. Let's say we have x as time 0, like at time 0, x0, and velocity or x dot at time 0 to be v0. I have a system, remember we are still in free vibration for the damping case. I disturb it a little bit, maybe by x0, and I push it a little bit by a velocity v0, and I release it. So the system starts vibrating. I have this initial condition, then I can substitute it here, solve the long equation. Let's say that we do that one, and you will get some ugly equations. And do the paste here. Okay. So let's see. I save the equation submit. Copy. So on your page, because I don't want to rewrite them, they are long. Oh yeah, I can paste them. Oops. All right. So you don't need to write them. You just write on your note that it is on page 39 on your notebook. Page 39 of your notebook. And it's there nothing, it's just some substituting this x0, v0 there and into equations and lots of math. You will get, for the tree scenario, zeta less than 1, zeta is equal to 1, and zeta is bigger than 1. Different answer. Why we will get different answer? Because look at this number over here, right? If zeta is bigger than 1, we will get a real number. If zeta is less than 1, we will get an imaginary number. And if it is equal to 1, the whole thing will be 0. So you will get different answer. The shape of the function will be different. Anyway, if we do all this math, we will get these three values here. Zeta 1, zeta is equal to 1, and zeta is bigger than 1. This is our response xt. You don't need to memorize this formula, and you just need to know that they are there. Even we may not even use them, but you should know where they come from and what they are. So now I want you to pay attention to few things here. Let's look at the number 2 and number 3. When zeta is equal to 1 and when zeta is bigger than 1. Can you see any sine or cosine in it? No, right? It is just an exponential. And that exponential, it has this negative sign there, e to power of minus something. What does it tell us? It's just going to exactly decay fast, come down fast. What about the first item? The first one, it has cosine and sine. So it tells us that there is some sinusoidal ups and down. Remember, we are still talking about the same system, like a system where I have like a mass and where is this pen? There's that one. So I have a system with mass m, stiffness k, and damping. If you recall, we said we are going to show it by this cylinder and piston shape. So hanging from the ceiling somewhere, we disturb it and we release it. So scenario number 2 and 3, so when we disturb it, it's going to come back fast to its original equilibrium position. Let's call this one equilibrium, and it's going to return there for us. So if we call this one, let's say X. But scenario number one is going to oscillate, right? Why? Because it has sine and cosine in it. However, this oscillation, we see there is another function here that we are multiplying by that one. It's going to decay slowly. All right? It's going to vibrate, but it's going to decay. Are you guys with me still? Okay. It is simple, that simple concept, but it's important to understand what's going on. As I said, the equations are not that important. It's just a lot of math to get there, boring math, in fact. But it's important to understand what's the physics. So the physics, we have this system, mass and damping system. K and M can have any value, C can have any value, but we know there is a critical value, which is 4mk, and depends on what this C is, this, we can have different zeta, because zeta, if you recall, was C over C critical. It can be less than 1, equal to 1, and bigger than 1. And the behavior of this system is going to be different, totally different. Like scenario number 2 and 3, when I disturb this system, doesn't matter how big my V0 and X0 are. Remember, this X0, V0 are initial condition. This system is going to move back to its original position, right, after some time. But if it is less than 1, the system is going to vibrate. It's going to go ups and down, right, because it has sine and cosine. But also it has to decay because it has this function e to power of minus something there. So let's plot them. Let's plot these three equations. Approximately, let's guess something. So this is, we call it X time. And this one we call it X or XT. So let's say I have X0, and later you will see on page 39, there is a MATLAB code which actually you plot them. But here just schematically, if we want to know the shape of this system, we start from X0 and I would get something like that when my zeta is equal to 1. I will get something like that when zeta is, for example, 1.5, bigger than 1. Zeta equal to 2.5. As I said, the shape, later you will plot them, you will see the exact shape, but this is what we will get. We are just plotting these three functions. So for different zeta, this is zeta equal to 1, 1.5, 2.5. So as you will see, as my zeta become larger, it takes longer for the system to come back to its equilibrium position, right? If I have a very, very large zeta, I disturb it, it slowly is going to come back to the system. This zeta is equal to 1 is the number that most of the, like the doors that have this shock absorber, they design it in a way that it has zeta equal to 1. Because when we open a door, we like this door to quickly comes back and close. So it has its own application, which we will talk about it later. But as this zeta is bigger, it takes longer for the system coming back, and the system is not vibrating. Maybe when I have zeta equal to 1.5, it likes to go a little bit up and then come back, like as I draw it here. But again, We will later plot them accurately, so we will see the function. This red one is the fastest one, okay? The fastest one to return back to its original position. So not that much of interest for, and this one, not too much vibration, because this course is about vibration and we like things to vibrate, right? So we can solve them. If we plot the first one, t, xt, so the system will see something. Let's say I start from x0. So the system is going to vibrate, but slowly comes back to its equilibrium position. Obviously, this is x0 at time 0 where I start, and the slope of that line is v0. Slope is v0, my velocity. Okay, so the velocity can be 0, so then no slope. And if I draw the envelope of this function, so if I draw the envelope of that function, all right, these graphs, the envelope on the bottom and top, let's move back one slide there. Take a look at this function, right? That should control the envelope, the amplitude of these ups and downs. So it is e to power of minus zeta omega n. That's the envelope of this one, how these things are slowing down, coming to 0. So this is for then any zeta less than 1. So obviously you can guess, the smaller this zeta it is, it's going to be more vibration. It takes longer for the system to come back to its original. If zeta is equal to 0, if you put zeta equal to 0 in this equation, you should get exactly the same function as we had before for a case when there was no damping, right? And obviously this system is going to have to vibrate forever and without any reduction. So later you can test, if you put zeta equal to 0 in this equation, you should get the same function that we had before. Any questions so far? If you understand so far, it means you're good. Okay, now we want to do one more things here. But before I do that, one more things. I have a question for you, and I want to see who is really in the class. I need my, okay. So remember we said when we have a vibration system, it has a natural frequency, and the peak to peak, we call the peak to peak the period of vibration, right? So like from here to here was t. Now my question is this Tn or something different? That's the question. When we have a system that vibrates, so just refresh your mind, just going to draw something here on the corner, because this is also important to understand. So when we had a system when it has no damping, I'm going to draw it on the top here for you. M and K. So this system, we would say x0 vibrates and the vibration goes forever because there is no damping, right? And then we said the distance between here to here is Tn, right? And Tn was 2 pi over omega n. This was time, like the time it takes to go from one peak to another peak, or one complete cycle. We call it Tn, and this Tn we could manage to find it based on omega n. Right? So now the question is, what is this T? Is it the same? No. And what it is? Look at this equation. What is your function? Is sine and cosine omega dt, right? What is omega d? It is omega n, the square root of 1 minus zeta 2. And we haven't decided for that. It is all math that when we solve this equation, we put everything there, we solve for a and b and all the constant, we ended up with this constant value in this sine and cosine, which turn out to be this value omega d. And this omega d, we will call it damping frequency. Let me write it down here for you. So omega d, omega n, square root of 1 minus zeta, it is called damping frequency. So here is the conclusion. When we have a damping in a system, the frequency of vibration is not omega n, it is omega d. And what is omega d? It is omega n 1 minus zeta squared, right? Remember, this is only for case when zeta is less than 1. When we don't have, when we have zeta bigger than 1 or equal to 1, there is no vibration, there is no omega n or omega t. So then this t, we will call it Td, and Td is 2 pi omega d. So is this Td bigger or smaller than Tn? Obviously, we look at omega d. Omega d is less than omega n, which means Td is bigger than Tn. Right? So Td always bigger than Tn. So it means that if I have two systems with the same mass, same stiffness, one of them with damping, another one without damping, when I disturb them, they start vibrating. But always the system with damping is slower. So you will see it takes longer to complete one cycle, which is obvious because the damping is there to slow down the vibration. All right, so it's very simple. We just introduced new concept here. And now you should be able to follow the next things that we are going to talk about. Or maybe I should stop here, because if I start, it's going to take longer than we expect. All right, so if you have any question, I can wait outside. Happy Thanksgiving, and I will see you on Wednesday.